In the last video, I talked about the Gibbs-Duhem equation. I said we have one more derivation to do, and that is the derivation of actually how to find or solve for the partial molar properties theta 1 and theta 2. I'm going to continue on with the Gibbs-Duhem equation and note that for constant temperature and pressure, for constant T and P, and I can say constant T and P because in the partial molar definition, T and P were both held constant variables. So for that Gibbs-Duhem equation, I've got dt is equal to 0, dp is equal to 0. Those terms both go away. The Gibbs-Duhem equation simplifies to just x1 d partial molar 1 plus x2 d partial molar 2 is equal to 0. Okay, so this is going to be an important equation that I plug in a moment. I'm going to go back to the original beginning and say that our first goal was to prove that this equation was true. So this is the weighted average of the partial molar properties is equal to the mixture property. All right, and I can say that if I want to take the derivative of the whole thing, I'm going to use the product rule. So d theta is, so take the derivative of the first one while holding the second one constant, and vice versa. Theta 1 dx1 plus x2 d partial molar 2 plus partial molar 2 times dx2. All right, now rearranging things a little bit, recognize that I've got a x1 d theta 1 and an x2 d theta 2, which are both being added together. So if I group those things together, I recognize that those have to sum to 0 by the Gibbs-Duhem equation, by Gibbs-Duhem at constant T and P. All right, so now I'm left with just these three terms. Next, I'm going to apply the physical constraint and say that x2 must be 1 minus x1 because they're mole fractions, and applying this to that derivative. So if I take the derivative of this, the derivative of a constant is just a constant. Derivative of x1 is a minus. So simplifying gives me d theta is equal to partial molar 1 dx1 minus partial molar 2 dx2. Oh, no, I simplified out for x1. So it's x, yeah, got rid of x2 in favor of x1 such that I can now factor this. So I can now factor out a dx1 and then divide to give me a differential equation. So d theta dx1 is equal to partial molar 1 minus partial molar 2. So I can solve for partial molar 2 by going back to this original equation that we started with and solving for x2. I'm sorry, solving for theta 2. So theta 2 is theta. Should be more specific when I'm saying theta because theta under bar is different than theta over bar. Sometimes it's hard to talk and think at the same time, though. There we go. All right, so I'm going to plug all this stuff in for theta 2 over bar, and then I want to solve for partial molar 1. All right, so I'm going to need some more. Try and do this yourself. I'm going to pause the video and do it and show you. So this equation that I just wrote, again, is this equation solved for theta 1 and plugged in for partial molar of theta 2 by solving this equation. To simplify this, I'm going to multiply through by x2. So I've got x2 partial molar 1 is equal to d theta dx1 plus theta minus x1 partial molar 1. And take this term over to the other side and note that x1 plus x2 must be equal to 1 by the physical constraint, such that I can factor out a partial molar property 1, and then I'm left with x1 plus x2, which is 1. So simplifying this whole thing gets me partial molar property of 1, which is what I wanted. I wanted an expression for this. is equal to the solution property plus x2 d theta dx1. And this is the equation that I used on the end of the video a couple videos ago. So I used this and I said I would derive it. This was the derivation for it. So I can do the same thing for partial molar of property 2, by the way. So I can do the same analogous derivation and end up with something like this. x1 d theta dx2. Okay, so these are relationships that you can use to calculate what the partial molar properties are. Of course, there's a problem with using these equations, and maybe you've thought of this already. But in order to use these equations, I've got a little bit of a chicken and the egg type problem. Because in order to use these equations, I need to know what the dependence of theta as a function of x1 is. So I need to know what the property is. I have to have measurements for this property. Right, but then another way to get around it is if you have experimental data. So say you're doing this to look at partial molar volume, for instance. You can mix several substances at different concentrations. So you can make yourself a plot. Okay, so how would you go about doing this? So say you're in a lab and you want to model what V over bar is. Well, you wouldn't want to be wanting to model that. You want to model the mix. All right, so what would you do for mixing water and ethanol, which is a highly non-ideal mixture? You would go to the lab and you would mix several experiments. So you'd try several different concentrations and you would physically measure what V as a function of x1 is. And you don't have to do the entire plot. So maybe, let's say that you have a graph here and you want to find out what the molar volume of the mixture is as a function of composition. So composition goes between 0 and 1. You could simply take some data points here and maybe you find that it looks something like this. As you start with pure component 2, your mixing property is going to be 0. And maybe you've got some non-idealities coming in here, and then you've got a curve for that. So next you would go and you'd fit a function for this. We've talked about several different ways that you could fit a function to a curve. So you choose however many parameters you want, and you would find your dependence of V as a function of x1 this way. So you'd fit a curve here. Then you could take the derivative of the property as a function of x2. Then find derivatives such as dv dx1. So the point is you don't have to do the entire curve, right? You can do as many experiments as you're comfortable with, but that's the idea. You're trying to get a relationship for the solution property, which is the underbar, as a function of changing what the compositions are. And then by using this equation, you can find what the partial molar properties are, theta over bar 1 and theta over bar 2. And then you can plug in finally to find that V1, this property is x1 V over bar 1 plus x2 V over bar 2. So hopefully that made sense, but what you'd want to do is a little bit of experimentation, and then you want to fit a model to your experiments, and that will allow you to calculate what your property is for any value of V within that range. One more thing to note is that these equations are kind of looking like the equation of a line, sort of. So this derivative term can be interpreted as the slope of this curve. So anywhere I want, let's say I've got x1 is equal to 0.7 or so. If I wanted to, I could take the tangent line at this curve. See if I can draw it neatly. Nope. Let's see. Take the tangent line at this curve, and that would tell me what my partial molar properties are. In other words, at x2 is equal to 0, so at pure x1, at pure x1, pure component 1, let's say, my mole fraction of component 2 is equal to 0, and my partial molar property for component 1 is equal to the mixture property, and vice versa. So I could take this tangent line. This tangent line is actually the slope of this curve, and I could figure it out that way. So I could say that the partial molar property of component 1, I wanted to make sure I'm saying the correct thing here. The partial molar volume of component 1 is on this side. So this is the partial molar volume of component 1 at x1 is equal to 0.7. So it's theoretical, right? So it's not, it has to be evaluated for a specific point because partial molar properties are a function of composition themselves. So this point is the partial molar volume of component 1, of pure component 1, at x1 is equal to 0.7. Likewise, so just in terms of variables, this is v over bar of 1, evaluated at x1 is equal to 0.7. And up here, I've got partial molar volume of component 2, of pure component 2, at x1 is equal to 0.7. That's up there. All right, that's enough for this video.